So we're now on chapter 23. Section 1 is about how low mass stars become, what happens to the white dwarf in the center of that planetary nebula. So the end of last chapter, the outer layers of this star slough off because the core decided to collapse. Well, remember, the core collapsed because the poor little star just couldn't get hot enough to fuse carbon and oxygen beyond carbon and oxygen. And so what happens to the core? It changes into something else that has a new name. We call it degenerate matter. So, in this star, the layers are, expanding slightly because of the temperature variation, and then the core no longer has fusion going on. So there's no thermal pressure pushing out. The gravity wins and the core collapses. When it does that, it becomes what we call degenerate matter. So this is approximately 1,000,000 times more dense than water, 200,000 times more dense than the Earth. So now we rename this core to white dwarf star. And this happens, electrons cannot occupy the same space. So they start pushing out on the inside of the star. And so electron degeneracy pressure, electron is highlighted because in a minute we're going to have a different kind of degeneracy pressure. But electron degeneracy pressure helps prevent the collapse of main sequence stars. It's pushing out along with the thermal pressure. But once we have a white dwarf, fusion is no longer occurring. So the only thing that is holding up that star is electron degeneracy pressure. Think of your room and how many people can you put in that room before everyone in the room goes, don't put another person in here. I cannot occupy the same space as the next guy. So electron degeneracy pressure is pulling out. The other one is two magnets. When you push the magnets together, they just won't get any closer. White dwarf material, degenerate material, is extremely heavy. Okay, we said it was really dense. It makes sense that it's really heavy. So a teaspoon of white dwarf star would weigh about as much as, a large truck or an elephant or two. So, a teaspoon of Earth weighs a couple of grams at most. So then this leads to this weird thing where the more massive the white dwarf is, the smaller it actually becomes. More massive means more gravity. Gravity pulls down and squishes it. So Chandrasekhar is how you say this name. This was a really important guy doing research on stellar corpses, white dwarf stars. And he did a lot of the research, and so there's some things named after him, like the Chandra telescope, which gives us a lot of the imagery that we're looking at in these lectures. So models of white dwarf structure show that, the smaller the mass, the smaller the mass, the larger the radius. And so as mass gets smaller, radius actually shrinks. Another one of those backwards relationships. So now we'll go on to the next one. So we get to the Chandrasekhar limit, which is really important. Make sure that you remember this. Quantum mechanics says that electrons cannot move faster than the speed of light. But as you squish on a material, the electrons on it will actually move faster and faster the more pressure that you have. And so as that white dwarf mass approaches 1.4 solar masses, remember that means the star is getting smaller and smaller, the pressure means that those electrons begin to move very close to the speed of light. And so when that star becomes more massive than 1.4 solar masses, the electrons are moving so fast that they actually blow up the star. And so 1.4 solar masses becomes the white dwarf limit or the Chandrasekhar limit. We will see this a couple of times before the end of the semester because this limit helps us figure out distances in this universe, actually. Helps us figure out the distance to faraway galaxies. But I'm getting ahead of myself. So this star made red giant a second time and begins to collapse. And so then the outer shells create the planetary nebula and reveal that core. And so it once again becomes hotter and brighter, spends some time, up here with a fairly relative brightness, but the temperature keeps going up because we can see more and more of the core, and then takes several million years for that core to cool off and collapse as it, gets older and older because there's no fusion. So it's just like, the hot coal after the fire that sits there and there's no flames, but for, hours, the coal continues to be hot and cools down and cools and cools and cools and cools. So the mass loss exposes the inner hot core. Star moves across the diagram because it's getting hotter and hotter during the collapse, and then cools down, and it will cool off for millions or billions of years depending upon the size of the white dwarf star, the mass of the white dwarf star. There we go. So a couple of images. This image from the Hubble Space Telescope on the right, image A. Here is Sirius A and Sirius B. The same image taken in X-ray shows us Sirius A. Where did my Sirius A? And Sirius B, the white dwarf, is much brighter in X-ray. So it is giving off a lot more energy, just not as much visible light. So we have to remember that visible light does not tell us the whole story. And so the next thing will be how massive stars die.